What you see here is a slow-motion picture of the cutting action of a planer tool. In planing, the tool remains stationary while the work is fed into it. As the work moves forward, the material shears and flows over the face of the tool. Here, the material flows naturally and the tool is cutting efficiently. Now, one factor that affects the way in which a tool cuts is its shape or geometry. In this case, the cutting edge is wedge-shaped. The base is angled away from the work, producing a clearance angle. This prevents the tool from rubbing on the work. The face of the tool slopes backwards, producing a rake angle. This controls the chip flow and the size of the cutting force. How does this compare with the design of other cutting tools? For example, a chisel. A chisel was probably the first type of cutting tool ever made. We can study its design more easily in a diagram. It has a wedge-shaped cutting edge. In a chisel, the angle of the wedge is called the point angle. It's ground to suit the material being cut. The clearance angle is formed by holding the chisel away from the work. And here's the rake angle, the angle controlling the size of the cutting force. Now, both the rake and clearance angles here are dependent on the angle at which the chisel is held. If the chisel is held at too low an angle, we get a shallow cut. What happens if the chisel is held at too steep an angle? Can you see what's happening? The chisel is digging deeper and deeper down into the work. A hacksaw consists of a frame which holds a thin blade under tension. The cutting action here is obvious, but the blade cuts on the forward stroke only. Let's take a closer look at the blade. It's made up of a number of teeth. In this blade, nearly 300 of them. Under a magnifying glass, each tooth would look something like this. It's a tiny cutting tool with a wedge-shaped cutting edge. There's clearance between the work and the base of the cutting edge, giving the clearance angle. And as with the planer tool, the face of the tooth slopes backwards, producing a rake angle. Each tooth has the same shape, the same rake and the same clearance angles. But there's something else about a hacksaw blade. The teeth are all spaced equally apart. We call the distance between each cutting edge the pitch of the blade. Now, blades vary according to their pitch. Here we have a fine, a medium, and a coarse blade. Which would you use for what? For example, which would you use to cut thin gauge metal? Well, the pitch of this blade is too coarse. It's greater than the thickness of the metal. Trying to cut with a blade like that could damage both it and the work. For a thin section, you need a blade with a fine pitch. Now, there's something about the way the teeth on this blade are arranged. What you see here is the edge of the blade. See how the teeth are bent over in groups, producing a wavy line. Do you know the reason for this? These are all lathe tools. They're each designed to do a different job. Let's start by looking at this one here. It's called a knife cutting tool. On the lathe, it's designed to feed into the work along the axis of the machine. Feeding in this direction, a cylindrical surface is generated. Can you work out where the rake and clearance angles are here? Let's stop the machine and take a closer look at the cutting edge. The clearance angle is down the side of the tool. Here it's called the side clearance angle. The rake angle is on the top side of the tool, the side over which the material or swarf flows. It's called the side rake angle. Now let's look at the cutting action again to see why the tool is designed like this. See how the side clearance prevents the tool from rubbing against the work? And look how naturally the material flows over the top. That's the effect of the rake angle. It directs the swarf away from the work and makes cutting easier. Next to the knife cutting tool, we have what's known as a parting off tool. On the lathe, this one is designed to feed into the work at right angles to the machine axis. The object of this operation is to cut off unwanted material or to sever a turned component from the rest of the bar. Let's wind the tool out and take a look at its design. In this case, there's clearance between the front of the tool and the work. It has front clearance. And to control the direction of the chip flow, it has a back rake angle. Can you think where else clearance is required here? So far, we've looked at the knife cutting tool and the parting off tool. But what about this one? It's called a light turning and facing tool. In fact, it's a combination of the other two. From this point of view, it has the geometry of a knife cutting tool. It has a side clearance angle and a side rake angle. From this point of view, it has the same geometry as the parting off tool beneath it. Here's the front clearance angle, and here's the back rake angle. Now, as the name suggests, we can use this cutting tool for turning. Here you can see the side clearance angle between the tool and the work. But look at the direction in which the swarf flows over the face. It's different to the knife cutting tool. Now, as well as generating a cylindrical surface, we can use this cutting tool to generate a flat surface. Again, notice the direction in which the swarf flows. We can find out the reason for this by looking more closely at its cutting edge. It has two rake angles, a back rake down here and a side rake down here. A combination of these two produces a rake angle in this direction, the direction in which the swarf flows.